In the today's class, we'll discuss about the vibrational spectra of the molecules. Let us take the diatomic molecule and how does this vibrational spectra of the diatomic molecule arises, that we will discuss in the today's class. So let us consider a diatomic molecule and which is going to continuously vibrate about the mean position, and therefore the extension and compression of internuclear distance between the atoms of the molecule takes place due to vibrations. So basically the internuclear distance between the two atoms in a molecule, then the distance between the atoms is going to extend and it is going to compress because of the vibration of the molecule. Okay, so atoms are changing their position with respect to their mean position. Otherwise, the bond length of the molecule is going to change because of the vibration. And this vibration gives rise to different energy for the molecule, and that gives rise to different vibrational energy levels. Let us take the minimum internuclear distance between the atoms of the molecule, which is called as bond length. So that is called as equilibrium distance, or it is also called as bond length of a diatomic molecule. The vibrational spectra are discussed by assuming the vibration of the molecule as a simple harmonic oscillations. So in UG level, we'll consider the simple harmonic oscillation of the molecule. If you go for higher studies, you will discuss about the that is anharmonic oscillations are also going to be considered. But in this particular semester, we'll consider only the simple harmonic oscillations of the diatomic molecule. So let us take the vibration of the diatomic molecule, and the distance between the atoms is going to change with time. So because of the vibration, the atoms are going to change their position with respect to the mean position. The vibration of the molecule can be compared with the vibration of masses connected by a spring. You assume two masses connected by a spring. If you disturb one of the masses, definitely that mass is going to vibrate because of the vibration of the spring. Okay, and you can define force constant for the spring and potential energy and kinetic energy transformation. Otherwise, the conversion of kinetic energy to potential energy and potential energy to kinetic energy is going to take place. In the diatomic molecule also, we assume two masses of atoms, two atoms are of masses M1 and M2, and they vibrate as a simple harmonic oscillator, just like a spring motion. Okay, here the distance between the atoms is going to be acting like a spring. The use of the reduced mass is going to be used, which is basically reduces the problem of two bodies into one body problem. In the discussion of the rotational motion of the molecule, we have discussed the reduced mass. Basically, reduced mass is the effective mass of the system. Okay, so it is given by M1 M2 divided by M1 plus M2, where M1 and M2 are the masses of two bodies. So effective mass is called as reduced mass. Basically, the concept of reduced mass changes the problem of two bodies into one body problem. We consider vibration of the reduced mass about the center of mass. Okay, instead of taking vibration of the two masses, we consider vibration of a single body whose mass is equal to reduced mass of the system, and its vibration about the center of mass is going to be considered. Then the frequency of oscillation of diatomic molecule can be given by new oscillation, new OSC. OSC stands for oscillation, that is going to be equal to 1 by 2 pi into square root of K by mu. And here K is force constant of the bond and mu is the reduced mass of the diatomic molecule. Okay, and here K is called as force constant. It is just like a spring constant, and mu is called a reduced mass, and which is equal to M1 M2 divided by M1 plus M2. It is called as the reduced mass of the diatomic molecule. So this is the frequency of oscillation of the diatomic molecule by considering the reduced mass. Once you find the frequency, we can easily find the energy of oscillation. So by considering the quantum mechanical vibrations, okay, the concept of quantum mechanics, the quantized vibrational energy is given by E is equal to V plus half into H nu oscillations. Okay, and here this energy is expressed in joules. Okay, this is the expression for energy in joules, and here H is the Planck's constant, nu oscillation is the frequency of oscillation, and V is the vibrational quantum number, and which can take the values from 0, 1, 2, 3, etc. So energy is quantized, energy is discrete because of this quantum number, vibrational quantum number. And here H is the Planck's constant, V is the vibrational quantum number, and V takes the integer values. That is V equal to 0, 1, 2, 3, etc. It can take the positive integer values, including 0. To convert the energy in joules to centimeter inverse, because already I have told you the spectroscopy is discussed in centimeter inverse units, that is wave number units. How to convert that joule into centimeter inverse? Just you have to divide the energy by hc, where c is the velocity of light in vacuum, which is expressed in centimeter per second. Then you can convert the energy expressed in joule into centimeter inverse unit. Okay, so I write the energy in terms of centimeter inverse. So this is the expression for energy in terms of joules. You express this energy in terms of centimeter inverse. So therefore, the vibrational energy in wave number units is obtained by dividing this expression by hc. So that will give you EV, that is energy in centimeter inverse, equal to energy by hc, where E is the energy in joules. If you do that, you will get EV is equal to V plus half into nu oscillation by C. So just you have to divide this expression by HC. H gets cancelled. You will have nu oscillation by C. Here, this is frequency divided by C is equal to 1 by lambda, because you know that the velocity C is equal to frequency into wavelength. So frequency by velocity, which is equal to 1 by lambda. 1 by lambda, that is reciprocal of wavelength, is called as wave number, that is called as nu bar. Therefore, I can express this energy as EV is equal to V plus half into nu bar, where nu bar is the wave number of the oscillation, corresponding oscillation. Now this is in terms of centimeter inverse. Okay, so here energy is expressed in frequency in centimeter inverse, and here energy is expressed in wave number in centimeter inverse. So centimeter inverse is the unit of wave number. Here V is vibrational quantum number, which is unitless. So nu bar is wave number, which is having the unit of centimeter inverse. Here we can take 0, 1, 2, 3, etc. So this expression gives the allowed quantized energies of the vibrational energy levels. Okay, so vibrational energy of the molecule can be obtained using this expression. So here we can take only integer values. Therefore, the energy of the vibrating molecule is quantized. It can take only discrete values or quantized energy values. Let us find out. So how this energy values can be found. Already we have obtained this energy expression. Energy EV is equal to V plus half into nu bar expressed in centimeter inverse. Here we can take the integer values. To understand the vibration energy levels and vibrational spectra, we'll try to determine the energies of vibrational energy levels. Okay, so that is for V equal to 0, what is the energy? That is E naught is equal to half nu bar. So put V is equal to 0 here, you will get V plus half, that is half into nu bar. So ground state energy, the lowest state energy equal to half nu bar centimeter inverse. For V equal to 1, the next possible value of vibrational quantum number is equal to 1. So E1, the first excited state, is equal to 3 by 2 nu bar. So 1 plus half is 3 by 2, 3 by 2 nu bar centimeter inverse. For V equal to 2, you get E2 is equal to 5 by 2 nu bar centimeter inverse. For V equal to 3, you will get E3 is equal to 7 by 2 nu bar centimeter inverse, and so on. So if you look at the energy values from one state to another state, they are having equal separation. First energy level is non-zero and it is equal to half nu bar. Second energy level is 3 by 2 nu bar. Next is 5 by 2 nu bar. The next energy level is 7 by 2 nu bar. The separation between them is equal to nu bar. Okay, so it is half nu bar minus 3 by 2 nu bar, you will get a nu bar. Okay, that is how separation between the energy levels is exactly equal to nu bar. Therefore, vibrational energy levels are equally spaced. We'll look at that. The vibrational energy levels and vibrational spectrum of the diatomic molecules are represented by this figure. So here vibrational energy levels are represented by this V equal to 0 gives you half nu bar, V equal to 1 gives you 3 by 2 nu bar, V equal to 2 gives you 5 by 2 nu bar, 3 gives you 7 by 2 nu bars, and so on. So distance between them is equal to nu bar. If there is a transition of the molecule from one level to the another level by absorbing the particular photon, definitely the energy of that absorbed photon is exactly equal to the difference between the energy values, and that is exactly equal to nu bar centimeter inverse. Therefore, pure vibrational spectrum of a diatomic molecule gives rise to a single line, okay, and whose wave number will be equal to nu bar, and that is utilized for finding the vibrational frequency of the molecule. Okay, if you know the wave number of a diatomic molecule because of the absorption of photon, definitely you can find out the vibrational frequency. If you know the value of wave number, nu bar is equal to nu oscillation by C. Therefore, you can find the vibrational frequency of the molecule. Energy of the molecule you can find out. Okay. The allowed transition of the molecule between the vibrational energy levels is given by selection rule, and for vibrational energy levels, the selection rule is given by delta V is equal to plus or minus 1. So molecule can make the transition from one level to the very next level. It cannot go for 0th level to 2th level, second level. It is not possible. So it can go from 0 to 1. It can go from 1 to 2, 2 to 3, like that. So change in vibrational quantum number should be equal to plus or minus 1. So plus 1 represents the emission, minus 1 represents the absorption. Here, initial value of V is 0, final value of V is 1. So initial V minus final V gives you minus 1. So this is giving rise to absorption. So molecule will go to higher energy level by absorbing the photon. Molecule can come back to the lower level by emitting the photon. So when emission takes place, delta V equal to plus 1, and when absorption takes place, delta V is equal to minus 1. So this is the selection rule for vibrational energy transition. Since vibrational energy level difference is a nu bar, so all energy levels are equally spaced, the separation between consecutive energy levels is equal to nu bar. Therefore, the wave number of the vibrational spectral line emitted or absorbed, that is a single line, which is observed at nu bar centimeter inverse. Okay, at a particular wave number, you can find only one line is observed, only one spectral line is observed if you consider the diatomic molecule as a simple harmonic oscillator. So we have to remember this concept, that is vibrational spectra of the molecule lie in infrared region. So you can observe the vibrational spectra in infrared region, and basically the vibrational spectrum or vibrational motion of the molecule gives rise to spectrum because of the change in dipole moment of the molecule. So change in dipole moment is the cause for vibrational spectrum. So finally, I will repeat this statement. You have to remember, change in dipole moment of the molecule is responsible for vibrational spectra, and vibrational spectra of a molecule is observed in infrared region of the electromagnetic spectrum.